Okay, clear. Okay, now let's start recording. So I think yeah, maybe it's better just to we're gonna just go over the questions for the exercise 2, and just mention some points that needs to be like kind of like important, or if you have question about that some of the exercises, just feel free to ask. And so I'm gonna share my screen now. Can you guys see my screen?
Yes.
All right. So this exercise is mainly about like function estimation and time series prediction. So quite straight. I think this is quite straightforward. So the first one, you just need to run this UI regress. Okay, and let me just quickly clean my MATLAB. We just run this, and you just need to so when you click data, and you can start to placing some data points, whatever you like, and then when you are done, you need to you can like stop the placing the data, and then you can just using different kernel here, and then you can adjust the like the hyperparameters of these SVR, and then you get different kind of like decision boundary basically. Okay. So I can let me check. So just quickly and go through those questions. So the first one is just like you just try the influence of using linear kernel, and then you just try different value of E, which is the arrow. I call it like arrow tolerance, and also the bound. Bound is basically a regularization parameters, which we have been seeing before. Like it's like just the gamma values. And so basically you need to try those different values and see how the decision boundary looks like. Okay. So basically you're probably gonna get something like this. So this is pretty much so this is a formula. I think it's important to mention this. So you need to make sure just to mention, okay, what is this when you're changing the E and changing the gamma here, which is the bound, so you know what is kind of like influence that you have for this based on this formula. And you can see that changing the E will basically just increasing this, how do you say, the margin of the decision boundary. And then, and if you just do the bound, which is the regularization, so it's pretty much the same like the previous exercises. So it's like it's trade-off between the margin and the number of the miss arrows. Like it's trade-off between the margin and the arrow, let's say. And then more like the higher the bound, the more like punishment you are giving to this kind of arrow. So your margin will be like smaller when you're increasing it. So basically, yeah, you get something like that. And the last question is like the sparsity property coming. And so basically sparsity properties means that, well, if you don't need it's like a property that when you decide the decision boundary, you don't actually need when you are given a bunch of data, then you actually just need a few of data to become the support vector, and then you need very few like data points to actually decide this margin, decide the decision margin. So this one can be observed, like if you see that each time you run this graph, you will get a number of the support vectors. So it means how many support vector are used to decide this boundary. So the less this number, the more sparsity property, I would say. So based on that, you can check like how you're gonna change the E or how you're gonna change the bound, this regularization parameters, and then how do you change that to make this like the number of this support vectors like become less instead of like 100%. Okay, so that's just you just need to answer that, I would say. Okay, so yeah, so that's basically the first one. Any comments on this?
No, thank you. It's clear.
Okay. And the second one, so it just needs to be, okay, you need to construct some data points, which is like not a linear one. So you just try different, you know, like you maybe try a sine or sine called like this very curvy one, or even this one you can try. And then you just need to choose basically, yeah. So let me just clear this. So you can just try something like, I don't know. And maybe you can already just like, you know, try to build some kind of data set, which is good for some kind of kernel. And as long as the linear kernel is not doing a good job, I would say that's okay. And then you just try different, you know, like kernels, and you just motivate yourself based on the, you know, you can, because you already have the visualization of the function estimation, and also you have this kind of like support vectors, the percentage of the support vector. So you can, based on those two, you can reason, okay, which one is the best. So, but there's no like this question is just something, yeah, just to telling you basically like there's better than some kernels, better than the linear kernel. Okay. So I don't know if you, so I asked the question to DA this morning about this because I was wondering what is the expectation for this problem, and they said, well, it's just, yeah, it's not so important, this question. So just, yeah, but just discuss what you see. Okay. All right. Does that any feedback on this? If not, we're gonna move on.
Yeah, I only think that they just want us to mention with providing some examples that we would be in some challenge in case our data set is not linearly separable. So we need to switch to some other functions.
Mm-hmm. Yeah. Yeah, I think that's a point for this question. All right. So this one. Okay, so this one, why SVM regression is different from the classical list square fit. And so for me, I basically just gonna go back to, well, I just discussed what is SVM regression, and also what is actually this classical list fit is, like based on some formula and also some explanation, basically. So your SVM regression is basically, you need to, the essential thing is like we need to decide this kind of like decision boundary, and you just make sure that like this decision boundary can include most of your data points you have here, and you're trying to minimize this kind of like function, and which is outside of the boundary, like the data points, it's outside of this decision boundary. And of course, and the classic list square fit is just, yeah, you just directly minimize this kind of like square arrows for everything, and you can introduce those kind. Yeah, so it's like, from mathematically speaking, it's just totally different methodology, I would say. So. So here, yeah, you can also, for the classical list of square fit, it's quite normal to apply regularization as well to avoid the overfitting. but essentially it's totally different formula, like for the minimization problem. Okay. So I think that's enough. I don't know what you guys think about this question. What else do you think we should mention?
Yeah, that's good. The TL also said in the session something about yeah, what you said, the cost function is mainly the difference, and it's based on the you cannot make the tube in the epsilon tube, you cannot make it on a classical least squares. So maybe that's another important thing to mention.
What do you mean, like the except epsilon? I'm not sure.
Epsilon tube, is that the tube that they're asking for, the E we are setting in the first question?
Yes. Yeah.
You cannot set that in a classical least squares fit.
Yeah,
So
yeah, that's true.
you will
Yeah.
always have, every point will add to the regression, so you will not be able to get something that's sparse. So maybe that's also relevant.
Yeah, that's a good point. So maybe you can see, like, yeah, because of this E, SVM have like better sparsity property than this classical square one. Well, basically, yeah, if you equals E equals to 0, then it becomes the classical one. It theoretically just becomes this classically square fit. And there's like, if you check the one we have before, so if you put, I actually did this, like E equals just to 0, and you get everybody is like a supported vector. So yeah, that's a good point to mention. So actually, because this SVM, SVR, we can call it even, allows E parameters. It can introduce like sparsity, I guess. Okay. So yeah, I think that's enough, and let's move on. So now we just go into this sinc function to approximate this one. So let's just go for the function here. So first, yeah, it's again, you need to try different gamma and sigma to basically to see which one gave you the best result. And here, and then yeah, it's yeah, you just need to run the code. I don't know if you guys have some problem with running this code. I think the exercise 2 is quite straightforward. There's no to so this one is, let me check, 1.2.1. Okay. Yeah, so it's like, yeah, this is just generating the data, and then you use this kind of like model again, and then you just change it to F, and then you use MSE here, and then you start to tuning your parameters, and then you plot, and then you calculate the error. That's basically how the code looks like. Is there anyone have some problem with the coding for this part?
No.
Okay. Yeah, so for this one, for first one, you need to try out different ones. So I'm gonna check what did I get. So yeah, you just need to try out different kind of like a gamma and sigma and see how it works for you, and just try a bunch of things. This is just an example of the visualization. And so you discuss this result, report and then you need to report this MSE for each combination of gamma and sigma 2. So basically, I try to draw this kind of like heat map like this, and then you can just, yeah, then it's like all the combination which is mentioned in the title here. But maybe I think I like put too much. Maybe you just need this tree, like gamma from 10 to the 10 to the power of 6, and this sigma, yeah, you just need the 3 times 3. I think I kind of like overdo it. So you get something like this. So the code itself, it's also, yeah, just running 2 for loop together, and then just calculate it, and then let me check which one has this code. But this is already Bayesian. Yeah, so I think the one which I comment out here. So you build a gamma list and build a sigma 2 list, and you just like calculate. You first automated this. You just giving this to, and then you just run this simulation for getting the gamma and sigma 2 first, like using this train one, this auto parameters, like tuning, get this alpha and beta, and then you just use simulation, this function, and just to calculate the output for the test. And you just like record the error. And then you just print it with this kind of like coding. If you guys interested in the code, how to get this plot, I can, yeah, like we did last time, we will put somewhere on the Notion pages so that you can have a look.
Of course, that would be very helpful. Thank you.
Yeah. Okay. So we got along with the first one, and so second one is like, do you think there's optimal hyperparameters for the problem algorithm Y? So for this one, basically, I also asked the TA this morning about how to answer this one. So basically, it means that, well, she says like one, because gamma and sigma 2, those are like hyperparameters. So once you fix those two, and then what this SVM is trying to solving a convex problem now for the parameters of the model. So those are two, gamma and sigma 2 is like the hyperparameters, which you need to like decide beforehand before you doing actually calculating the parameters, which for the model. Okay, because those hyperparameters is actually, so for each combination of these parameters, there will be always a convex problem, and there will be always like optimized like parameters for the model. The point is, but the point is like this hyperparameter is something you choose beforehand. So it's like something, how do you say, it's something unclear or unknown, like whether even choosing this parameter is also a convex problem or not. This is like, you never know. So yeah, you cannot be sure that, because normally for a convex problem, you will have one optimal solution, but here you just don't know this. You cannot be sure that this hyperparameter, like optimizing this hyperparameter, is gonna also be a convex issues. So you cannot, but maybe it is, but you are never you're never sure of that. So that's why you use like some kind of like research or whatever, like tuning algorithm to actually find those hyperparameters. Does that make sense? Or because, yeah, this question is kind of like confusing.
Yeah, that I didn't understand that also at first, but like she also mentioned that the W's and the B's are also parameters. Like those can be optimized, and that's what you're doing with every algorithm. But the hyperparameters, there's no way to specifically optimize. That's not what the procedure or the model is is doing. So you're probably getting, as you said, some local optima. But yeah,
Mhm.
I had some with that as well.
Yeah. I think, but I think you can actually use the result from the previous one because previous one you are just gonna get this kind of like heat map. Okay. Let me check the word. So you will get the heat map like this. Okay, so it's like so I think one is 10, 10, 30, and 10 to the 6 power of 6. But you can see here that even some of the combination, they are pretty much giving the very similar results. So I think somewhere even they are very close or something. So so you can maybe saying that yeah, based on this result, you can see that there's no you cannot see this problem as like a kind of like convex problem or something, and then it's not somewhere. Yeah, maybe based on your results, you can. I think you can maybe mention about this. It's like because when you are choosing, so once you get this heat map, actually you can then based on this, you are using it for the hyper. Then you use this heat map to kind of like guide you to select the appropriate like hyperparameters. So, but in the beforehand, you don't know about this. So you have to actually do this kind of like the investigation before you choose your hyperparameter. So it's not something like automatically happens. Okay. Okay. All right. Okay. So should we move on? Okay, let's move on. So then this one is basically you need to choose the gamma and sigma 2 using this automatic tune function. And then you need to compare the results and also the hyperparameters using both the simplex and grid search algorithm and report difference. So this one, I think it's also quite straightforward. Sorry. So let me check what I write here. So yeah, so you just basically, just create some table and you do research and you get this gamma, what do you get for the gamma and sigma 2, and also note down the MSE. And then you do another kind of like investigation saying, okay, yeah, so you just do this and just record those two. And maybe you want to get this like the calculation, maybe get the average of the MSE and also gamma and sigma 2. So check this. And then yeah, well, it's about, I think it's totally depends on you what you want to discuss. And then like I would say they're like the performance are both fine. But maybe the simplex is getting better results, like using the MSE. I think MSE is better, like, but it's like very small difference. So yeah. So yeah. So I think yeah, based on you can see, I don't think this one is very critical, and then you just discuss what you have been seeing. Okay. Should we move on?
Yes, please.
Yeah.
Okay, the next one we need to discuss is Bayesian framework. Well, Bayesian framework, well, first question is the question you need to discuss like in a schematic way about how parameter tuning works. So based on this Bayesian framework, how did you actually get those two the parameters? Like for example, for the alpha and beta, gamma and sigma 2, basically. So I think you can just directly you can just directly steal something from the lecture. I think this schematic is quite nice for explaining what is like the three level of a Bayesian network, a framework. And basically, yeah, you need to just say, you need to explain which level is doing what, is trying to like tuning which kind of like parameters. You need to explain what is the first level is doing and the second level is doing. And third level, what is this like, which parameter is tuning? And basically, yeah. So you just discuss this, and then I think it's just basically explanation. And of course, the code which is mentioned here, yeah, it's just like first those 3 lines of code. I would say it's like the one you need to kind of like interpret it here. So first you tuning the parameters for the model, like for the alpha and beta. And then you get the regularization term, which is one of the hyperparameters. And then sigma 2 is more like a model parameter. So it's like higher than the previous two. So yeah. Then it's corresponding to the schematic, I would say. And then yeah, I think that's pretty much about it. I don't know if you guys, I don't know what do you guys think about this. What else do you think we should include here?
Yeah, I'm not sure. I just run the code, and as you said, the part on the lecture on what each level is doing sufficiently explains. Maybe I haven't gotten into the detail because I haven't written anything.
Okay.
Yeah, I understand the general idea of the levels that are being that you're going level by level, setting each parameter that best results. I remember we had a discussion with a TA about this exercise, because depending on where you start, you have to first, like for example, if you're going to start setting the alpha and beta as the as the code writes it, you have to define a sigma squared. Even if you are afterwards going to see which are better gamma and sigma squared, you do have to use some parameters to define previous your alphas and betas. So like the results are going to be different, and depending on which initial parameters you set. So you have to maybe choose those correctly. He didn't say we had to do it now, but like it's an idea of how this this method works, because right now we're using 0.4 and 10, but like why would we use those if they're not optimized?
Yeah, it's a question of like the chicken and egg. Yeah? It has to start somewhere.
Yeah.
That's
yeah,
like
but
yeah. That's actually one of the, I don't know.
We could iterate over
Go
different values, but yeah, that sounded like too much. So
so actually for me this sounds like really like the I don't know if you guys know the acceptation and the maximization like algorithm, like EM algorithm, you know. So you start with some kind of like the initial algorithm, initial parameters, and you try to maximize the likelihood, and then you just like you just keep doing it, like literally doing this kind of like iteration, and actually it will. So what then if you do this like multiple times, well, it will bring the hyperparameters, like even it starts somewhere very low, like giving a very bad result, and after like kind of like a few after some iteration, it will help you guide you to the like the like better hyperparameters basically. I think
that's a great analogy on bioinformatics, right?
yeah.
That was
Because this Bayesian things, I think they are having the same kind of like nature, I would say. Close tier, you know. But anyway,
makes sense.
so anyway, I think, yeah, I mean, maybe you will find out more when you actually try to study the lecture again. And you look at your lecture notes, maybe you can find more information, which kind of like explain more details and why. But we're gonna just stop these right now because I don't think, yeah, right now we are still like I said, maybe when you are writing a report, you find more information and you want to add it up. But for us right now, I mean, we are only few people, so we are not we are not. I don't think we're gonna discuss this very seriously. You know, we just
don't worry.
Yeah. Okay. Okay, let's move on. So for this one, automatic relevance determination. So basically the idea is try to find out which kind of, because you are getting like data with a lot of inputs and you want to see which input has better influence or relevance to the output result. So you're basically trying to figure out which input is like have the best like relevance basically. So then they kind of like they kind of like develop this kind of algorithm, this method for you, and you decide and then you basically gives you the selected and the ranking, those two outputs, like to decide to tell you, okay, which input is doing better, which input is more relevant. Okay. So I think what I did here is I think when you run the code, so it's 0.2.2, I would say. 0.2, no. 1.2, no. 1.3. Yeah, so when you run this, is this one? No, this is still the Bayesian. Oh, yeah, I think it's here. Yes. Okay, let me just clear this one. So you run this block to generate your data, and you just run this one just to just get which one is better. Okay, gamma. Oh, wait a minute! I just run everything. Okay, so here you see that this one, this function, you need gamma and sigma 2. So yeah, which needs to be tuned. So actually, basically, I use a result from the Bayesian framework, like the optimized gamma and sigma 2, to run this. Okay. Basically, what you're gonna get is something like this. So let's see this. So select and the ranking is what you're gonna get. And from this, like the input here, you already see that actually, yeah, the Y train, X train is just some random stuff. And then Y train is actually using the X train, the first element, like first the input, you see here, to add some, and it just add some random noise. So from this one, you can already anticipate that the first one will be the first input will be the most relevant input. So what you get here, so you get a kind of like this selected and ranking. So if you go check what is selected, it's selected 1. And then the ranking is something like 1, 2, 3. 1, 2, 3. So it's like just saying, okay, maybe and it's just saying, okay, when you the first input is having the number 1, and second one number 2, and third one is number 3. Okay. So if you change this, let's say let's change it to the number 3 input, and then you try to run everything again. And you see that the ranking is actually saying, okay, yeah, the first what's come to the first one is 3 now. So your input, the third input is actually the most relevant one, and the one otherwise is others. And the select, now you see something like, okay, actually 3, 1, they select the third input, and the first input is the most relevant one. But actually, yeah, but I'm sure why this one is here, but I don't think it's, well, if you just stick with the code which is provided in the PDF, you will just get 1. So I think, yeah, I think now you should have an idea what this one is doing. And then it's like, so you need to visualize the results in a simple figure. Well, yeah, because it's just the, which input has better, like is it like the first most relevant or second relevant? So for me, I just plot like a bar chart, something like that. So it's just saying, okay, this one is just the first. We have some more people join. Okay, so that's, I think, well, you can do this something totally different. This is just my way of doing it. Yeah. So any remarks here? I think this part is quite straightforward. I think you guys should have some question about this. And second one, okay, so second one is like, okay, if you don't have this one, you don't have this function, you don't have this Bayesian framework, okay, what do you need to do to actually to figure out which input has better selection instead of this Bayesian framework? So this is something, if you, so I look it up, and I was trying to basically trying to mimic the way we are trying to do with the Bayesian framework. And so this is just my idea, okay? I don't have an idea. This is just for its inspiration, I would say. Not sure whether this one is correct or not. And so I think I kind of like find this somewhere on the, I think this procedure is actually, I think, yeah, it's, I read the text, the text part about this automatic relevance determination. So I was just trying, I think this one is mentioned in the textbook somewhere, or even maybe it's even mentioned in the slide. But this is my adult version of like not using this Bayesian framework reasoning. So my idea is like, okay, you're giving a training data with an input, and you need to figure out which one is the best, or and my way of doing, like, first you just need to, yeah, like do it to normalize the inputs, like with real normalize the input, like with zero mean or unit variance or something, and then you just try to remove the one, like from the one of the input, kind of like so you remove one input data, and you trying to so you can start with the first one, and after you remove that data from your training set, just use cross validation to evaluate the MSE error with the same hyperparameters. So we are just saying, okay, if we get rid of the first one, how is the with the same kind of like hyperparameters, what is my errors on this data set? Okay. So my point is, okay, if the first one, like for example, I equals E1 right now. So if if let's just imagine a very like ideal cases. Let's just say, okay, actually the only the first one is actually the only input which is related to output. So if you just remove this one and you are trying to use the rest of data, which is maybe completely noise, and you are trying to figure out a way to do the functional optimization, then I think like logical, I would say then you're probably gonna get a very big error rate, and if you let's say if you now and then you did it for if I equals 2, so and then you just remove the second input, which is, let's say now second input is just totally noise, and then you keep the first one, which is a very relevant input. So I would suspect that maybe this time the error will get lower, because now you already have this very important relevant input in your data set now. And then after this cross validation, then you're probably gonna get a lower MSE error. So you did this for everyone. You just loop through all this input, and then you figure out which one, and you just say, okay, which after removing this input, you get like the highest error rate you have, and then you can and then you can say that, okay, this is a very, like in this iteration, it's the best, it's probably the most relevant input. So you just identify after running the first iteration, then you just and then you just figure out the most important input. Okay. So and then so this is part also just we find out the one with the lowest one. Oh, I think it's highest. Sorry. Yeah, this should be highest. This is just a typo. And then you go back to step 1 again, and then just keep doing this, until you have the last one, and then you will get a kind of like based on like which one is removing first or removing at last, and you can already get an idea of which the ranking of this relevance, I would say. So so that's basically how I'm thinking. I don't know if you guys have other ideas, or you have other inspiration for this.
I just need to mention that for your explanation number 2, it's not just one input, but folds of input. For instance, if it is normally a 10-fold cross, therefore our input, or the whole data set of input is divided into 10, let's say, slices. So we remove one slice of input. It's not just one single input, but a set of a fold. So it is, we can rename it to a set of slices of inputs that we kind of ignore them. We take them out, and then we do this whole training on it, then do the validation with that slice which has been ignored. And then we put it back and take the second one, then repeat it again.
Mm-hmm. Yeah, so it's like kind of like I mean, it's kind of like the idea, like but now they're still different from the cross validation, right? Like it's not some fold, now you are talking about we're just gonna remove the whole data without that input, basically. So it's like it's kind of like similar like we did with the cross validate, like the 10-fold or whatever, but it's still, I mean, it's very similar, but it's not exact. It's totally different things,
I understand that the function of the cross validate right now would only be to find the best sigma squared and gamma for each different option of inputs. Like if I took one input out, I still would want the model to evaluate to its best possible evaluation. So it's more of a tool for the model to rebuild itself in the best way than actually making the idea of faults in the data. But that's how I understood it. Like I'm seeing what you said, Linya, and it sounds really like I actually saw this in statistical data analysis in model building, and it sounds exactly like what they're recommending for deciding if one variable is important or not in linear regression. So it sounds really really accurate. But I'm not sure if I'm misevaluating what the cross-validate should do, because it's important to
So one of the doubt I have, I mean, cross-validate, if you think about exercise 1, it's cross-validate. So what you get is like you are trying to evaluate model performance with given hyperparameters, okay, like the gamma and sigma 2, and you use, like, if you just call the cross-validate function, like from this SVM like toolbox, so it will tell you like what is the MSE for that. Like you're gonna get a like cost function after the cross validate. Okay, I mean if you gave it like the hyperparameters, and of course you can also keep using that automated like a parameters tuning method, like tune SVM with SVM or something, and then it will just tells you like how basically, it will basically tells you like how the model performance basically, okay, with either with like the fixed hyperparameters, or you are trying to tune this hyperparameters, something like that. So it's basically, when you call this, so cross validate, it's just tell you, okay, you have a way of evaluating your model performance, like something like that. Okay. So so this one, I think I kind of like well, because I was when I was trying to answer that question, I was trying to look at the textbook and about this. So I was looking at the textbook about this automatic relevant determination, and I think I found this like the very, I just basically copy paste and just to trying to switch some concept for that, like switching, just changing something, and then I don't know, maybe later on I can have a look at it again and just say like, maybe I don't know if you guys have the so I think it's here. I found it here, like it's actually this, I mean, the step I was mentioning here is basically kind of like I tried to modify this based on the LS SVM input selection by this automated relevant determination. So I was basically just trying to mimic that like steps. I think it's mentioned somewhere like in the lecture. I don't know. I think there is a slide about this. Let me check, just quickly check we can find it or not. But basically, it's just like I think when you look at the slide again, and then you probably will see what I mean, what I was trying to do here. Go to my study. Quickly check if we can find that slide or not. So I would suspect somewhere here. Bayesian, not Bayesian. Oh, maybe it's here. What's the content? So here it's talking about ARD. And let's see if we can find it or not. Oh so here, so this is basically the text for this. Okay, so this is the step which I was trying to copy. Okay, so you can have a look at this, and also I'm just gonna make sure I just screenshot this and put it here just for you guys to just to have just to see how it works, because this is based on the Bayesian framework. Okay, you see that there's still like a different level of kind of like inference, and then I was trying to mimic this. All right. Okay, so I think this one definitely needs some deep understanding before you to try to reasoning about this. So I will, yeah, I think this is the materials you should look for. Like just I think if you understand this one, then you probably with this kind of like my kind of like hints, maybe you will, yeah, maybe you will try get understand what's maybe is there some way else to do this, but I don't know what you guys think. Maybe we can continue on the other because yeah, we need to hurry up.
Yeah. As far as I know, up till now, this part is not related to cross-validation. I mean, the whole definition of cross-validation is something else, something different from this part for ARD.
Yeah, but you see that the question is like they ask you, okay, how do you do that with cross-validation? So you need to try to kind of like using the like use what this cross-validation can do, and then you need to basically cross-validation, you know what to do, and then you need to achieve, like you need to tell which input is the most related input. So, yeah. I mean, you understand what you want to do, so it's totally your idea, your work to yeah.
Yeah, I understand what you said. The way I do is just I would explain that in case I want to do cross-validation, then I would just, instead of doing it, I would replace the whole process of ARN with cross-validation, which is kind of different. I mean, it is similar, but the procedure is different. So we need to, as I told you, so we have segments and I guess you know what cross-validation does. So the way I will explain it is that, okay, I will now replace cross-validation with ARN. And instead of Bayesian framework.
Okay. All right. Yeah, that's if you guys, I think this is something definitely we need to look up to. Well, so let's not spend too much time on this. Let's just move to the next one because we still have some things to cover. So let's try to finish this soon, like in half an hour, I would say. Okay. So that's okay. Now we are done with this. So now it comes to the robust regression. Well, basically, it's kind of like just discussing what is a non-robust version of the model and the robust version, and then basically it's trying to test to you like what the model will do if there are some like a ridiculously outlier. So basically the robust version basically gonna ignore those outlier and just doing what we did, and the non-robust one will actually get a very huge influence for the outlier. So if you see this plot, this is one with the without the robust version. This is non-robust version, and you see there's some outlier here and here. Okay, and you see that this originally this should be like it's just gonna be a sinc function. Now it's kind of like twisted by this outlier. And here is a result of the robust version. So basically, everything still stay the same, and those outlier, they don't seem to give any impact on this functional estimation. So you need to compare, discuss the results. Well, I think you also need to explain how this non-robust version works. And here you also need to explain why you are using the MAE and instead of the square MSE. so this one is somewhere also discussed in this in the slide. So I think I kind of like copy this slide here. So this is something from the slide. I think maybe, yeah, you can find it. So you are seeing here, it's talking about the cost function here. And then you talk about two kind of like the model of the noise. One is like Gaussian and another one is Laplacian. I don't know how to pronounce this correctly, but anyway. So it's correspond to kind of like an estimator for the cost function. So L2 is the one with square, and then with the square one, and then this one L1 is the estimator, is like the absolute error. And here also, this is from slide, and it's saying that okay, the least square, the L2, which is this one, is less robust against the outlier and the null Gaussian noise. And that's okay. This you can, yeah, this is from lecture, so I think you can just see this. And the SL1 estimator reduce the influence of the outlier, while the outlier are too much emphasized in the cost function of the L2 estimator. Okay.
Yep, exactly.
So yeah, so then you can just use this to answer this question.
Exactly.
And then of course here you ask you to try different kind of like weighting function. So I also asked this question today on the with TA, and they are just saying okay, yeah. So if you you can go to this menu user guide to find something like this. So you can find the difference. What is actually those like this weighting function looks like inherently? What is their definition? And then so based on my result, I would say yeah, all this kind of like weighting function doesn't make too much difference. Yeah, like it doesn't cause any big difference from the performance, I would say. So yeah, that's end of the story. All right. So this part, I think, yeah, it's quite. If you find the information is quite straightforward. So for this robust regression. Any comments on this?
Yeah, no, as you said, it's almost quite clear if we refer back to the course notes and the guideline, LSSVM guideline.
Yeah. Okay, let's now move on to the homework. So basically, we're trying to do this kind of like time series prediction with two data. So the first one is Logmap, Logmap, and then second one is a Santa Fe. I don't know. Yeah. And okay, so basically, you need to first, you need to learn a model based neural LS SVM model, and to for this prediction. So you need to use and you need to kind of like define a strategy how to tune this parameter. So gamma and sigma 2, so which you already know. And this other thing is like how many inputs that you need to actually for the model to produce produce a prediction, basically. So and you need to get a strategy to do this. Okay. So first one, I also discussed. I also asked this question to TA this morning. So yeah, more or less the strategy is like first you just fix the order number. You just fix this, and you are trying to figure out. You use like the automated like parameter tuning for the gamma and sigma 2, and see how much, how low the MSE can get with the test set, and based on this, you can draw a graph and seeing which order is giving the best, like the lowest MSE error. And then yeah, and based on that, you just choose your order gamma and sigma 2 and see how it's time series prediction. And yeah, so basically you're gonna get some I would say you probably need a plot like this, just saying, okay, yeah, I have this order from 0 to 100, and I pick some point, and which one is giving the lowest error. So in my case, it's kind of like order equals to 50, and then basically, yeah, you need to discuss what is strategy that you use to do these 3 parameters. And then you just use this parameter to do some prediction and to plot the whatever things you have, like you got. Okay. So yeah, so that's basically it. Don't know if you guys have any comments on this. Mm-hmm. Okay, so if not, so we're gonna move on to the next one. The next one is actually again another data set. So again, it asks you, okay, you whether order equals 50 is gonna be also good for in these cases. And so yeah, you just you just copy the code from this one you did and just try to draw the similar graph before. So you need to draw this graph with the arrow versus the order. So in my case, I will get something looks like this. Okay. So, and I will probably I would definitely not saying that the one with this one, like the 50, is this, let me check. Maybe this is not my my final plot. Let me check my final plot because but you get the idea, right? Like you just need to do this again and to just figure it. Yeah, you need to just fix the order and order parameters, and then just to see which one, and then you have each order parameter already have a value for gamma and sigma too. And then check where is my figures. And this is question. Yeah. Okay. Yeah, so I think what I gonna actually input here is some plot like this. So you see that actually, well, in the beginning it dropped, the arrow is dropping very significantly, and then it starts to. So here you can choose the order very large now because your Santa Fe data is like having like 1,000 already the data points. So you can try more orders from 1 to 1,000. You can try. And so basically what I get is this one is like here is just 20. So the corresponding order is 20, which is giving the lowest MSE and the MSE and the MAE. And then yeah, so I just say, okay, choose order equals 20. And then if I choose this one with 20, and this is corresponding gamma and sigma 2, you get something looks like this. And so yeah, so now it's, yeah, for me, I would definitely just answer order equals 50 is not good in this case now. And then I think what I also show like here, it's like you need to just, you find the order and you find the corresponding gamma and sigma 2 and do this kind of like time series prediction and just visualize and discuss your result. And here this is question I also asked TA this morning, and then so it's like, it would be sensible when you're training the model and trying to optimize those parameters. Do you think you need to use the good sensible to use recurrent prediction instead of like fixed prediction? Maybe it's different. It's a very, how do you say, not a good way to say it's like fixed prediction. So if I just illustrate what I mean by that, so paint. Okay, so for so there's one prediction you can get. So you have this better color sign. So you have, let's say you have data x1, x2, x3, and you are trying to predict x4. So you have like, this is have like order of 3, and you are trying to predict the x4. Okay, but notice that x1, x2, x3, x4, you basically all know them as, because you use them as a training set. Okay, so you already know them. You know the actual value, and this is a predict value. But you are actually already know this x4. You already know what this what this actual x4 value is. So basically what that's mean by the recurrent one is like, okay, even you know this when you predict the x4, x5, sorry. So this is recurrent predict. So when you predict the x5, so you are using this x2, x3, and this one which you just predicted with x4. And however, when you so you use this one to try to use this to train as an input to train a model. But however, there's another way. So you do the prediction, but then when you actually next time when you try to predict the x5, you are just directly using what you know about x4. So to put it in your model, to use it to train your model, basically. Okay. So so basically the question is asking, okay, does when you're training a model, does this actually because actually what we did here, like the code was doing, like as we just did before, they actually are using this one. So you are using just like all this known input and to train the model, instead of like you use the prediction from the previous one to use it as the input to train the model. So you need, so they're asking why you are not following this one, and what is does this make sense or not? Okay. So basically from TA we can see that, okay, TA was saying that first of all, so though both method has its pros and cons. So of course, if you are using the prediction for this, it's actually more real life, because when you are actually using a model to do the actual performance, actual prediction, you are actually facing this case. Okay. But however, those kind of prediction actually will have the good chances that introduce like very like your model, which is getting trained, is actually less stable, and it will introduce some risk to your model if you are using this kind of like way to train your model. Whereas like you use it because you already know something is already like the data is actually and you use them for the training, it will be more predictable, and you can be, and you have a better like what is this model can do, the pattern that you can follow basically it's more like the model which is trained by this way is more, how do you say, more like stable and maybe more like expandable, like than this one, basically than this training method. Okay. But I think yeah, I think in most of the cases, based on the exercise we did before with the neural network, most actually cases when you are training your model and you are training your hyperparameters, you actually just prefer use everything you know. And then when you are actually, then you use like when your training of your model is finished, then you use the model to just apply it on the data set and just to do the prediction and recurrently and just see how is actually the performance. So yeah, I hope I understand. So in a way, so what I agree, in my opinion, is that when you're training your model, just use this, okay? Don't you? And when you are trying to evaluate your model with real life, you want to see how it really works in real life, in the real life problem. Then you just use this recurrent prediction to get your like a model, real life model performance. Okay. I hope that is clear. I don't know. Does this is this clear? I mean,
Yeah,
I mean,
I think it's good.
Yeah.
Yes, no, thank you.
Okay. Okay, let's conclude this workshop, I would say. And you guys, so this is the last chance that you can ask to bring up a question to discuss, because otherwise I will gonna just stop this recording.
Thank you so much, Neil, for taking the time to explain everything. I really appreciate it.
Yeah, thank
Yeah,
you guys.
thank you as well to attending this workshop. Yeah, for me, it's like it's also a good opportunity for me to review all the content that we study. So it's good for me to review this. But yeah, I hope that because this. Let me just stop.